Okay, so it seems we are about to start. Radek, can you see my screen now?
Yes, I
Can you
can
see?
see your
Okay,
screen. Yeah, I
okay,
can see the
okay. So
presentation and your nice face in the web
thank you very
camera.
much. Not as nice as yours, and we will definitely have to cut this off, right? After this introduction. Anyway, I think everything is set. So let's make it. Let's take it easy. Let's do what we can do, and let's show let's show what we have.
Mhm.
So it seems it's like it's almost time. So I'll give it, let's say, one last minute, and then we will start.
Okay.
Okay. So people are coming. So yeah.
Mhm. Okay. So maybe just click into the presentation. We can
I
see
will.
yeah, now it's nice. There was the
Actually,
Windows
this is the
panel on the bottom
yes. Yes. Okay. I see. Windows
on now
panel,
it's
and
yellow. Yeah.
this is today's webinar. The simulation driven optimization.
So
I need to get rid of this camera. Yes. But people can see us, but we will after the initial session we will switch the camera off.
Yeah.
Okay. And maybe it's really the time to start the webinar, right?
Yeah. Let's
I
go
think
for
it's
it.
time. It's time. So let's go for it. So let's make a 5 seconds break. Hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar, which is called Simulation Driven Optimization for Turbomachinery. It's for turbomachinery applications. And yeah, welcome. We would like to show in this webinar how to set up a simulation driven workflow. That means that a lot of simulations are being like run in a loop, and they are converging to the best possible results. And yeah, so yeah, welcome. The webinar is being recorded, and the recording will be later made publicly available on our YouTube channel. So feel free to make yourself comfortable and see the webinar recording sometimes later. And yeah, I hope all the techniques work. And I think it's time to start. There will be a couple of sections. So in the first part, I will give a general introduction to the software, to the workflow. I'll say then a couple of necessities. And in the second part, my colleague Radek Maca will show some technical aspects, a little bit of hands-on, how it looks in the software. And in the last part, there will be a Q&A session, which is dedicated to your questions and our answers. So feel free to ask your questions. We will do our best to answer them. We will answer all of them. The most representative questions will be answered right away in the webinar, and specific questions will be answered later via email, but you can be sure that all the questions will be answered, and we are looking forward to them. Okay, so I can already see a question, so let's take a look. It's a good test. Yeah, Gregor's, yeah, hello, hi, hello everyone. Yes, okay, so at least this works. And I think we can start. So let's ask Radek if he's there. So knock, knock, Radek, are you with us?
Yes, I'm here. Hello. Hello to everyone. Hello to Luboš.
Okay, so are you ready for the webinar?
Yeah, I'm ready.
That's great.
Very in short, I'm ready.
Okay, it's perfect. Okay, so I think we can really start. So I'll go ahead. We will switch the cameras off, and we will come back in pictures for the Q&A session, I guess, maybe.
Yeah.
So I'll switching the camera off now. Okay, so I would like to start with an invitation for the couple of next webinars. The next webinar is a big one, a big day. What a day. At CFD Support, we will release the new TCAE version on November 9. So everyone has to come because it's a really big thing. Again, the best version ever is coming on November 9. We will introduce the new version, new features, new capabilities, new licensing system and everything. It's gonna be fun. We were working on this again for a lot of months, a lot of effort and time has been spent. So the new version on November 9. The next webinar is about centrifugal pump, CFD, FEA, FSI, and optimization on November 21. And the external aerodynamics webinar on December 5. And the last webinar this year will be about Kaplan hydro turbine on December 19. So feel free to come to our next webinars. And yeah, as you know, CFD Support is Czech Republic company, private company located in Prague, Czech Republic, located in Prague, and founded in 2009. We deal with CFD, FEA, FSI optimization and acoustics at all levels. A lot of kind of simulations. Primarily, we develop software. We call it a comprehensive simulation environment, which is called TCAE. It's a system. It's a system of plugins, which is extremely flexible and extremely usable. You can do quite a lot of it. You can set up your own workflow. It definitely fits an existing workflow. You can use any part of it. It's extremely flexible and a lot of fun. And the best of it all is that TCAE is unlimited. So the users can be sure they can use their resources to the fullest. It's focused and accurate because it's not software for everything. It's software focused on turbomachinery applications and external aerodynamics. So it's very important. It's focused and accurate software. It's been tested very, very extensively in the past. We did tens of benchmarks. A lot of them are available publicly. The software can be used on any device. It can be used on laptop, PC, cluster, cloud. It can be used remotely from home, from office, in Linux, in Windows. The same workflow everywhere. So it's very powerful because again, it's designed to allow its users to use their resources to the fullest. It's extremely efficient for this reason. It's based on open source. It's based on, in fact, more than 60 open source projects. So as you know, here at CFD Support, we have mastered the process to take the open source, integrate it, and turn it into the professional industrial tool, which is usable on real cases, which is important for our users. So we have spent so much more than 40 many years of development in a team, and we've spent enormous effort to put everything into the graphical interface, into the systematic process that it's now a high level CFD simulation tool, and much more, of course. And it has a couple of modules that's maybe not that important, but at the moment, but I will definitely switch. We invest all the profit and everything we invest back to the development, and we are developing a new module which is called T-Base. We didn't make it to release it in the next release, so it will be released in the next version, hopefully in the early next year, and it will be a really great tool which allow users to create the databases of their results and then use machine learning and create their own surrogate models. It will be a really big thing. It's unbelievable how efficient this is, but it's the little bit of future. And let me start with today's webinar, with the topic. So it's the optimization. We believe that the optimization is a really big thing. We believe it's a paradigm shift. It's a shift from trial and error method. That means 10 years ago, we were used to clean the geometry, set up the model, and set up the simulation, and run the simulation, and look at the results like one time in this process, and it was pretty much it. But that's what we called trial and error method, right? We tried something, looked at the results, and when it was good enough, we used it. When it was not good enough, we started the process again from scratch, but we did everything manually. But we believe that now the optimization it's a process. In fact it's a conceptual search for the best possible, right? So it's truly a paradigm shift. It's a new level of using numerical simulations. And let's talk about it, right? So we believe that we are engineers, and we believe that the world consists of parameters. At least the world can be described with parameters. And there are a lot of parameters everywhere. So the system is extremely complex, right? We can imagine that any CFD or numerical simulation has more than 200 parameters. All those numbers everywhere, all those schemes and turbulence models and everything, and then the mesh, and there are plenty of parameters everywhere. If you consider that any industrial product like a turbine pump or compressor has another perhaps hundreds of parameters, that it makes altogether definitely hundreds of parameters. And that makes us thinking about a multi-dimensional problem, right? There are multiple dimensions. Let's say we are talking about hundreds of dimensions, which makes the parametric space extremely large, but extremely complex and large, which is impossible to navigate with trial and error method or random actions. It's absolutely impossible. As you know, a human mind can imagine like 3 or maybe 4 dimensions, right? But definitely not hundreds, and that's a problem. That's why we should be smart, and we should use a computer for this. So the parametric space is extremely complex, and it has to be a machine which makes the decisions and which iterates in such a complex system. So optimization process definitely has to be done by a machine, and it has to be automated. And also automation avoids human error and human limits, etc., etc. But it has to be an algorithm. That's for sure. Yeah. So we here at CFD Support we developed this optimization module. It's software module. We call it TOpt, and it allows to create an optimization workflow. So it allows its users to set up a process where, for example, the meshing is involved, CFD is involved, FEA can be involved, or acoustics, or any other software part can be involved in it. And you can, with this, you can set up a workflow which iterates over the results. So what you need to do is to create an objective function, or sometimes we call it optimization function, which is the quality of the result you want to have. So typically for a fan compressor or turbine, it's the efficiency, right? So you want to improve your machine for the efficiency, right? And you can set a couple of parameters you are interested in, and you can change them on your product, for example, and let them change. And according to the optimization function, the objective function, the results are based on the results. The new set of the parameters is created, and again the new simulation process is done, and again new set of parameters and new simulation and new set of parameters and another new simulation. And with such a process, you can iterate towards the best possible results, to the best possible objective function, which could be the improved efficiency, for example. So this is extremely powerful thing, and it's definitely cannot be done by a human mind because because of the complexity and real numbers and everything. So in a short description, it's a system of simulations running in a loop and moving towards to the best what you can have. So that's what we mean with the optimization, specifically simulation-driven optimization. And yep, we have implemented two algorithms for the optimization methods into TOPT. So the first one is called golden section search, and it's I would say pretty simple but effective. And the other one is called direct, which is much more comprehensive, and it also can find the minimum of or maximum of functions, of the objective functions, and helps us to navigate through the parametric space. What maybe I should have mentioned, I'll go a little bit back in the presentation. The workflow is extremely flexible. So for example, if the user wants to use his own external optimization tool, like another open source tool like Dakota or something even more sophisticated, it's definitely possible. All the workflow is perfectly scriptable with Python, so you can join in the workflow, for example, the external optimization tool, optimization algorithm, which suggests new sets of parameters. If you believe it makes sense. Or for example, and that's very important, you can put in the game geometry builder, which based on parameters creates the new machine. So for example, in the past we have had great collaboration with CF Turbo, for example, or with cases, or with another open source tools, which we will show in this webinar. So there are a lot of options what you can do. So the workflow is extremely flexible, and it's always important what's the goal of its user, and we are definitely ready to help with the setup. So yeah, the geometry builder is very important part of it, and the external optimization is definitely possible. And by the way, also it's possible to run a simple mode like design of experiment to really see the set of simulations based on parameters and parameter changes, or you can use the optimize mode, which really iterates over the results towards the best objective function. So there are a lot of options, and it always depends what is the goal. It's number one is the goal, always the goal. What's the goal of your project? And anything can be optimized, any parameter, including the machine or numerics or whatever. So it's extremely general as well. So it's not just a shape optimization or what, it's extremely general. Okay, we have a couple of examples we would like to show you. So the first one is axial fan optimization. So we created a workflow which uses T-mesh meshing, TCFD, CFD simulation. The geometry builder is here OpenVSP. It's open source, which is very useful, so we can recommend it. So it's open source, which allows you to create geometry from the parameters of such for example, of such axial fan and TOPT. So such a workflow has been used and run, and yeah, so this is what we would like to show you. So much more information is available on our website, so maybe we will come back to it later in this webinar. But on the website you can find so much more details. There were 4 parameters. I think they were the chord of the blade, number of blades, I think the blade angle and blade thickness, these 4. And we have created this you can see in this scheme of the workflow. So the initial geometry was meshed in TCFD. Then it was simulated. Meshed in TMesh, simulated in TCFD, and then using TOpt, it was new set of parameters was in every iteration was suggested. OpenVSP created new geometry, and again the new geometry was meshed, simulated, and based on the results was running in a loop, and such a loop has ran 400 times. So we made 400 iterations, and then we stopped it and looked at the results. Here you can see the animation where you can see how the geometry was changing, what was the how the parameters changed over the simulations, and also how the objective function, which was the efficiency here, how the objective function was changing. And then here you can see for example, the blade profile here, and yeah, the meridional view and front view, and also the optimization function, how it was iterating over time. And yeah, much more details can be told about this, but as you can imagine, there was found a set which gave us the best possible for these parameters, the best possible set of parameters with the highest efficiency. Yeah, I'll go ahead. I'm sure there will be questions. What's very interesting about the optimization all the time, that with a human eye, you will never ever recognize what machine is more efficient than the other one. I have a quick example. We have picked 4 pretty random images of 4 impellers of this axial fan. The first one has efficiency 36%, and the last one has the efficiency. It's the highest one. It's the best. It's the winner. It's the best impeller. It has efficiency 46 or nearly 47%. The point is, with the human eye, you never recognize which one is better, right? This one has 40. This one has 42. This one has 47. With human eye, you will never recognize what's the efficiency of it. You have to run the simulation, right? And also when you run a lot of simulations, you have to have a tool which tells you, okay, we are getting better this way and this way and this way, and to iterate in multiple dimensions to the best one possible. So it's a little example that we need this, and it has to be an algorithm, and it has to be a machine, and it has to be run in a loop, because otherwise the human mind can't do this. It's simply not possible. Okay, so that's the axial fan example. We did the same thing with the centrifugal fan. So centrifugal fan optimization tool, again, the story is the same. We have put this geometry into the parameters. We did it here at CAV support. It was the Salome. Salome can be also run on the background and give you the geometry based on the parameters. So we did this centrifugal fan, and again there were let me see, there were 5 parameters: number of blades, angle, also the curvature of the blade, width of the impeller, and blade thickness. And again, we were looking for the best possible efficiency, and we ran I think 300 runs, and it iterated to the best towards the best possible, and at the end we have received the winning set of parameters that gives you the best efficiency. Again, something which is not that sophisticated when you set it down, but it's impossible when you do it by heart or with the human mind. And I guess this is the last case I wanted to show you in this session. Again, the similar workflow. we have created this for the propeller of the drone. So drone propeller, we have we set again the objective function, and we let it run for a couple of runs, and yeah, pretty similar case. It iterated, and at the end it gave the winner, which was the set of parameters and winning geometry, which had the best. I think this was lift torque ratio. It was not this time. It was not the efficiency. The optimization function was lift to torque ratio. And here I see the mistake, because it was it was OpenVSP. What was the geometry builder? So OpenVSP created the geometry every time based on the parameters. That's very important. Okay, so for this, I think this would be pretty it from me. I would ask Radek if he has a couple of something what he's going to show us. Radek, hello.
Yes, I'm still here, and I have something to show you.
That's perfect. So the stage is yours.
Okay, thank you very much.
Okay,
And
I'll switch
now,
over to you.
okay, and now you're right.
Yeah.
You can see my screen. Not yet, I guess.
No,
right?
no, we can't see it yet. At least I can see still my screen. So what's the?
Yeah, the same on my side. And now I think, yeah.
Now we can see it. Okay.
Okay,
Again,
perfect.
we can see it.
So thank you, Luboš, for this, for the first part of this webinar. And in my part, let's say with next 15 minutes, let's say, I will show you some simple examples of what TCAE and TOPT is capable of. So as you've seen, the general optimization topic is really complex, and to prepare or to show you some complex optimization for a real turbomachinery geometry is a matter of maybe hours to present it into detail. So I have take one of our examples, some simple example, we can call it test example on the piping system. And I have prepared, let's say, two scenarios. So first scenario, which I would like to show you, is that we take the external geometry builder, we do a geometric optimization, and let's say then for the best design, we can do some optimization based on CFD parameters, because basically, as Luboš already said, including CFD and geometry, every part of the workflow consists of hundreds of parameters, and basically you can optimize any parameter within the workflow. So in this case, I would like to show you what is possible. So maybe I will start by opening one of the case I have prepared. The first one is directly delivered within the TCAE. So if you would like to try it on your own, you can ask for a trial license, download and install TCAE, and then within the delivery, you can create it or test it, this case, on your own. So I have put it on my disk here into the webinar. Maybe I can show you directly. If you go to the installation folder here in tutorials, here you will find some basic tutorials which you can directly try, or more of them you can find on our web pages. So I will take this parametric pipe. So I will open it just to go through it. Right. Okay, so this case consists of a geometry builder. So first of all, what you need to do is to preset the standard workflow. So you will create the mesh. You will import the geometry from your geometry builder here from kind of this piping system, where we optimize the shape. We would like to optimize the shape to have the lowest pressure drop, and the parameters are given by 2 cross sections in the given places, and we will optimize the radius of these 3 cross sections. So these 3 radiuses of these 3 cross sections will be our optimization parameters, and what we would like to achieve is to have the shape which has the lowest total pressure drop. So, or yeah, right. So this will be our goal. So first step is to prepare the geometry. So I will not too much into details. So you will prepare the geometry, you will generate the geometry, prepare the computational mesh, you will generate the mesh, just look if the mesh is okay, then you will go for the TCFD part. So you will preset the CFD simulation in a standard way. So you preset all necessary things like fluid properties. So here we have a water, so piping system for the water, and you will set boundary conditions. So here we have 5 meters per second at the inlet, or you can set the flow rate for which you would like to optimize the shape, and run the simulation. And whenever you are confident with it, then you can move for the optimization. Yeah, so anytime you can enable the optimization module, like here in the manager, and go for setting up the optimization module. So I will now jump for my setup. So I think we are here, if I'm correct. Yes. So this is the preset case for this webinar purpose. So I simplified the setup, and let's go through it. So if we look at the optimization module TOpt, then there are just several menus. If you go from top to the bottom, like in a wizard, we don't miss any important parameter. So first one is the operation mode. So you can go for a simple DOE method. So you just describe the parametric space explicitly. You will define the values of each parameter to simulate, and then you run it. Or you can go for the optimization, where you can choose the method as Luboš presented, the built-in method, or you can put the external one, so you can connect it to Dakota or any in-house code or any other codes. And in case of the built-in method, there are 2 algorithms, golden section search or direct. So here we go for direct, which can search for the global minimum or maximum depending on the setup of the optimization function. Then in case of geometry builder, so it means if the geometry builder is external tool, external application, which has to be connected. So for this connection, there is an initial script for this purpose implemented, where you need to prescribe using a Python interface how to run the external tool, provide the parameters, and connect these parameters from TOpt to the geometry builder. I don't want to go into much detail because each open source each external tool requires different outputs. So then this script can be tailored directly to the needs of the external geometry builder. So if I a little bit jump, so here we define the optimization parameters. So we have 3 parameters which we define here. We call it R1, R2, R3, which is the radiuses of each cross sections, which is then delivered by this list. So these parameters are then taken as the arguments for running the external tool. So in this case, the geometry builders is just our in-house code written in Python, which generates such a geometry based on the input radiuses and position of the cross section, which can be defined externally. So basically, the script just provides, it takes it takes the optimization parameters, and it delivers to the geometry builder to generate new geometry for each optimization loop. If I go a little bit back for the max runs, it means how many runs for the whole optimization process can be run. So in case that the built-in algorithm don't find or doesn't find the maximum or the optimization, the maximum of the target value of the optimization function, then it will stop the generation, because sometimes based on the accuracy and based on the optimization tolerance, it's not you are not sure that it will be reached within 100 or 1000 iteration, and you have a limited time to to have the results, so you will just set the maximum number of runs. So in this case, in this very simple case, we have this optimization parameters. Here we have the tracked quantity. So here I define the built-in quantity which you can choose. So these are the quantity which TCFD directly evaluates. So you can directly use them as an evaluation tools, or you can use a custom one, and again by a script you will connect to any other quantity, or you can compute your own quantity based on some other parameters, whatever. So this is the track quantities, and based on this track quantity you can define the optimization function. So in this case the optimization function is simply the total pressure difference, denoted by this name. I would like to look for the maximum because the value is negative, so it's a pressure drop, and these are the tolerances to stop the optimization function. But in this case, just to be quick as possible, I suggest 12 runs, and the whole process works as follows: that for each parameter you define the minimum and maximum to each for each parameter. You can choose if the dependency of each parameter is linear, logarithmic, or you can explicitly list the values you want to simulate, or values which can given parameter has. And number of samples means that first the optimization algorithm needs to have some rough overview of the parametric space. So it basically, number of samples means it creates equidistant points in this interval, in these two, so the boundaries basically of this interval, and for each combination of each parameter it will create a kind of DOE optimization first, or not a DOE optimization, just a DOE run, and from this run then it will start to optimize the, or look for the best combination of the parameters to optimize the call function, the optimization function. So here we have 2 for each, so we have 8 simulation like a DOE, and then 4 simulation to find a better shape. So I think everything is clear, and when I run the simulation, so here in the graphical user interface, you can then watch for each simulation. So here you will see the results for each run, so for each combination of the parameters. Here in the browser you can see the shapes for each run. So for example, this is the run 1, this is the run 2, so this maximum radius at this cross section, and here you can list for the total pressure difference in pascals. So this is done for each point which is preset, and as a result, if I go back to the report, maybe I can make it larger, and finally when all the runs are simulated, then TOPT report is generated, in which you can read all the data which were simulated with all the values and all the combination of the parameters, and then you can see the function of the optimization function with respect to each run, or you can go to directly see the influence of each parameter to the optimization function. And after these, let's say, just 12 runs, we find out that the best optimization function point was the 10th run. So here in the blue we can see the DOEs. Yeah, it's just the boundaries of the interval or on the parametric space, and then these 4 points the algorithm suggests to simulate, and from these it finds the best simulation point. So it is the 10th point. So if you go to the TO browser, so we definitely we would guess that this shape is not optimal, right? And if you go to the 10, so this looks very nice. So this is something we would expect that it would have a good pressure drop value. So here we have seen that the final pressure drop is around minus 300 pascals in comparison with these weird shapes. For example, the second was or the third. So here you can see minus 5,000, and for that, yeah, for this one, for example, we can see minus 7,000 pascals of this shape. Okay, and typically what we do, if you run hundreds of simulation, we would like to have some not super fine mesh, or we need to also optimize the mesh parameters. Even we know that the accuracy is lower, but we are short on time, and we would like to simulate 1,000 iteration, for example, or optimization loops within few weeks, depending on the size of the problem. And for example, in the next stage, what I would like to show you in this, let's say, artificial scenario, is to take the best efficiency point and now look for the real CFD parameters. I mean, real that we would like to simulate with a finer mesh, which should be more accurate and basically see the really final total pressure difference for this shape. So we can prepare a new case. Let me see. Okay, this is the original one, and I think, yeah, here I have the very similar case where I loaded the CFD geometry from the best efficiency point. So this shape is available, so I load it into the new project. I preset again the similar simulation parameters, the same in the CFD. So I basically just copy paste the CFD parameters to simulate the same scenario. But in the TOpt, what I have changed, that I went just for the DOE. I don't need any initialization script, because now my optimization parameter is the background mesh size. Yeah, the background mesh size is simply some kind of proportion of the cells from which the final simulation final mesh is created, and this basically, this number defines how fine the mesh will be. So I additionally add, because my original TOpt was simulated without the boundary layers, which from the point of accuracy is very important. So in this scenario, we added the boundary layers. We have some basic refinement, and in the TOpt, we would like to refine more this background mesh size. So basically, we are increasing the number of cells, decreasing its size, which should increase the accuracy of the simulation. So I have preset 5 examples with the background mesh size, and again I just watch for the total pressure difference as a result. So here I have no optimization function because I'm just doing DOE. And if we look on the shape, So we have, yeah, on the final TOPT report, or we can again go step by step. So for example, the first run generates the mesh of size, where you have it, just 20,000 cells. And for example, the last was with 1 million cells. And now we can compare in the TOPT report, we can compare these 5 simulations with different mesh refinement. And if we go to the delta p tot, so we can see that for this finer meshes with boundary layer, we are going up to the pressure drop of, let's say, 480 pascals. And for example, if we, roughly speaking, about the setup of the meshes, we are pretty close to the constant value, we can call it. Or we can say, if with further refinement we are not achieving better accuracy, or for example, yeah, the results, the integral result doesn't change so much, so we can roughly say, okay, so this refinement is enough for my goal accuracy, depending on the goal. And based on these two optimization, we can find one of the best shape. Even we know that with rough mesh we don't, we have, if you do the optimization with the finer mesh, maybe the result will be a little bit different. But for sake of the time optimization, or for the whole simulation time, let's say, we can do it on the rough mesh, and then just evaluate the best efficiency point with a higher accuracy. So basically, any scenario of your workflow of the optimization chain, you can create with the TCAE and the TOPT itself, and the applicability is really huge and wide. So everything is available, and it is highly customizable to connect to any external codes or any other parts of the workflow efficiently, and by few, let's say, few case setups, you can achieve what you need. So maybe, I think it was more than 50 minutes, but let's say I would like to conclude with this example, and maybe it's time for next some kind of general discussion on and your your question.
Indeed, Radek. Thank you very much. I'm coming. So
Okay.
yeah. Thank you, Radek, for your part. It was sometimes it's there is a little bit I mean a lot of new information for a lot of people, so it definitely needs some time. And let's move in the webinar. So now I would definitely like to ask the audience to ask your questions, and we will do our best to answer them. So please ask your questions. It's your time, and we'll do our best. So let me see what we have, because I think that there were some questions. So please ask. We will pick those which we think they're relevant, and we will answer them right away. So Marco is asking which OpenFOAM version is applied. So by default, we use openfoam.org version. We typically are like half a year late to the latest developments, and we update over the time I would say in quantas when we think it makes the perfect sense. And we look, of course, everywhere else if something important is available in any OpenFOAM, in any other OpenFOAM version, and if it is, then we definitely keep an eye on it. So it's this, and also the question is continuing. The solver is pressure based. Yes, it's pressure based. A simple method, and this is too specific question about the total temperature. We can no, it's not constant. It depends on which solver you use. But anyway, this is it for now. Yeah, will you share the recording? Yes, the recording will be shared. We will send it to you. That there's an automated email which comes with the recording, and it's also tomorrow. I think at latest in the afternoon it will be on our YouTube channel. So you can feel free to visit our YouTube channel. There is webinar playlist, and there will be certainly the webinar recording where you can check all the details. And anyway, you can come anytime later, and we will do our best to answer the questions. Charles is asking whether the simulation is simulating fluid. Yes, of course, it's fluid dynamics. The core of it is fluid dynamics. The of course, yeah. Look on our website. You would be able to see a lot of applications in the case studies. You can see any of them can be downloaded and used and loaded directly in the latest version of TCAE. Bistrik, hello, is asking what global optimization method is implemented. If I understand right, this the direct method is looking for global minimum or maximum. So the direct method is for global extremes. If I understand the question. Okay, and yeah. So feel free to ask your questions. We will be here for a couple of whiles. What I wanted to mention, we only mentioned so far. We only mentioned the positives, right? What are the benefits and positives? There are definitely issues connected with optimization. I would like to mention a couple of them to be fair enough. To be fair, just fair. So it's optimization workflows are extremely complex. So you should know very well your goals. You should know your goal, what you want to achieve, what you are looking for. That's extremely important. Unless you, when you don't know where are you going and what is your goal, then you will very quickly get lost in the lot of results, because it's easy to generate a lot of results, to create a mess, and it's definitely very easy to get lost in a lot of in that mess, in a lot of results. So you should know well what's your goal and where are you going. And also in the beginning you should have somehow developed a trust into the results. So because Radek's favorite saying is garbage in, garbage out, right?
It's not mine, but
but you like it
I
so
like
much.
to say this. Yeah.
Yeah. It tells pretty much everything, right? If your simulation is wrong, then no optimization loop helps you at all, right? Because then everything else is wrong. So you have to really build a trust to your results. You definitely should make some comparisons, make some estimations, whether the simple, the base case, the baseline case is what you would expect, and then you can up to it. You can build optimization workflow, because optimization brings so much much extra complexity. It makes everything so much complex and so much more difficult and hard than it was in the trial and error method in the beginning. So be careful with it, but definitely it's a way, and it's a nice to have things developed and optimized, because it's really a thing which it doesn't grow on trees, right? It's really it's a technology, and it's very nice and deep, sophisticated technology. What else, Radek? What's up?
Yeah, and maybe I would like just to add that also, in addition, that is really complicated. What works for the base geometry doesn't work for the corners of the parametric space. Yeah, so if you have some complicated shape based on some of the parameter, which makes the simulation domain strange in some way, that there are small gaps and so on, which are not available for the base geometry, then you need to also take care about these scenarios, right? Because sometimes it can, for some parameters variation, the mesh generation will fail, for example, and this can be also taken into account, right? Because the difference from the base geometry and some point far away in the parametric space can look pretty strange in sense of the geometry shape, and for this the mesh parameter should be also prepared. So typically what I do is that I create a baseline, then I create some very strange shape I would like to simulate, so typically some optimization point, this geometry connected to the geometry shape at the edge of the parametric space, to just check if my workflow is robust also for simulate these strange points in the parametric space. So it's very complex.
It's pretty complex. So definitely, I would say it's not for beginners, let's say, but definitely we shouldn't worry too much and be afraid too much of it. But it's definitely it's the double-edged sword, let's say.
Yeah, and also we are here to support, right? Them.
Yeah, absolutely. Yeah. We're definitely here to support you in your first workflows and understanding. And it's, again, I'll say it again, it's like riding a bike, right? It's like riding a bike. If you ride a bike first time in your life, you're very likely not master, right? But after some time, everyone gets into it, and everyone can ride a bike at the end. It's very similar, but it's all about the practice, right? It's the practice. The practice makes masters. So it's all about the practice. So yeah, work with it, and that definitely makes sense. Okay, I can see one more question from Pierre. It's when you said that Salome or OpenVSP it was used, is it included in the ticket module or needed yourself? Well, OpenVSP is packed together and it's completely available in the TCAE. Yes, it is. And Salome is not, because it has 9 gigabytes, right? Only the installation file. So it wouldn't make any sense. And be careful about Salome. It's compiled per individual, kernels for the distributions in
version,
Linux,
yeah.
and so there are a lot of versions. So it's impossible to be supported. But OpenVSP is nice. That's Python based. So it goes very well together with the TCAE. So OpenVSP is packed, and also these. At least I think the propeller is included. The propeller tutorial is included in the TCAE installation, so anyone can try the tutorial right away. It's pretty simple. And yeah, also what we didn't say in the webinar, the geometry builder is very typical bottleneck of the optimization workflow, right? To set up a new optimization workflow is extremely simple. It's basically what you have seen, what Radek did. But to create the geometry builder, it's the bottleneck, right? Because it's up to you how many parameters. Every engineering office has different habits, different experience, different point of view. Use this fillets, don't use them, use this diameter, and all the drawings, engineering drawings are different in every engineering office. Then every geometry builder is different in every engineering office. So so it's a mess. Yeah, and that's why and I'm also answering partly the question from Pierre. The ticket module is basically consultancy project, right? So we discuss ticket on individual basis with every user, because it's the only exception in the modules, because every engineering office has so much different expectations how things should be done. So there's nothing like universal geometry builder for pumps, for example. There are similarities for sure, but there's nothing like universal thing. So this has to be discussed individually, but don't worry about that. All the people get there if they want to. Support is technical support is extremely important, and that's us, right? So we are not just software vendor. We are the whole safety support environment. It's a family-like environment which helps where everyone helps everyone, and the knowledge and know-how transfer to the users is extremely important, and it's part of the game. So it's not just a code software. Code makes nothing. It's the experience and skills and patience and know-how together with the software make the results and make happy projects. And what else? I think this is gonna be it. It's gonna be it. It's 4 p.m. On my clock. So let's conclude. So let's move in the webinar. Again, here are not so much updated couple of those who already share our visions with us. So any one of you is welcome to join us on the journey. For us, it's a pleasure. It's our job, and definitely in a way, it's our mission. So anyone is welcome. And now we would like to thank you for your attention. Let us know anytime in the future. We will do our best to support you in your projects. And Radek?
And thank you for your attention.
Yes,
thank you, and
for your
we are
attention.
looking forward for your question, or if you need to discuss anything deeper, just contact us and take care of yourself. Yeah,
absolutely. Thank you everyone. We'll leave you with that. Bye bye for now. Bye bye.
Thank you.